Okay, now these are the worked examples from exercise 6.5 before that exercise. So we did look at this question in class. We looked at, remember this is displacement versus time. So the first question was, when is the particle at rest? Now the particle will be at rest when it's not moving, in other words, when the velocity is zero. And we spoke about this in class, and the velocity is zero when dx dt is zero. Now dx dt, or velocity, which is dx dt, is the gradient of the displacement. So it's the gradient of the displacement versus time graph. So we're looking when the gradient of this graph is zero, and the gradient is zero at t3 and at t5. So the particle is at rest at the stationary points on this graph, which is t3 and t5. The next question was, when is the particle at the origin? Particle is at the origin has got to do with displacement, and that will be when x is zero. So particle is at the origin when x is zero, which means at these places on the t-axis. So therefore the particle is at the origin at t2, t4 and t6. Now for part B, we didn't get to finish this today. So when is the particle moving at its greatest velocity? Now, a velocity again is the gradient of the displacement versus time graph. And we can see that we've got here, where the gradient is positive, we've got positive velocity. Here we've got negative velocity, which just means that it's travelling in the negative direction. And here for this part of the curve, because the gradient's positive, we've got positive velocity. Now the steepest part of the curve is actually through here. That's where it's steepest. So however, it is travelling in the negative direction. So if you've got, so this is definitely travelling faster down here than it is there. So, and there. So this is the steepest part of the graph. So what I would do, sometimes in some questions, if you're getting a positive and a negative answer with the same magnitude, if they ask for the greatest velocity, you need to be very clear and just state that yes, the velocity is greatest at this point, however it's travelling in the positive direction or the negative direction. So the steepest part of this curve will be where this inflection is here, because notice we've got concave down, concave up at t4. So we'll say, well, the velocity is greatest there, but because this gradient here is negative, the velocity is greatest, however, the particle is travelling in the negative direction. So the greatest velocity is at t4, where the curve is at its steepest, however, it is travelling in the negative direction, because for this part of the curve, dx dt is negative. Now the example 2, it says the graph below shows the displacement x of particle over time t. We can see at time 0 that the particle is at the origin. Then we seem to have negative displacement up to time 1. So with all of this, the particle is moving to the left of the origin, because for example you'd have negative values of x down here. So the particle is moving to the left of the origin and then it stops, and then the particle is getting closer and closer to the origin because the x values are coming back and they're closer to 0. So back at time 2 the particle is at the origin, and then for these other times along here you've got positive values for x. What you've got to think of is that you've got values of x along here and values of x along there. I'm just going to draw this on a page and show you. Again, just imagine that there are values for displacement here, for example, 1, 2, 3, 4. For example, down here you might have -1, -2. So at this point in time, the displacement is -1. Let's say at this point in time, displacement's -2. Remember, I've made these values up. So if I was to draw this on a straight line, this is what happens with this particle. Here it starts at the origin. Then I'm going to put these points here. Then at this point in time, it's at the position -1. And then at time t1, it's at the position -2. So the particle has just gone from there to there. This is what the particle's done, from there to there. This is at the beginning, and this is at time 1. That's where the particle is. Then the particle is now back at -1, so it must have returned back. And then here the particle is back at the origin. So what's happened with this particle is that it's moved to the left from time. So the particle, so from time 0 to t1, the particle moves to the left. It then stops, because it has to stop. turns around and moves to the right. To the right. Okay? And it moves to the right from T1 to T2, where it reaches the origin. So back at time T2, it's back at the origin. Then what happens? It's +1, +2, +3. It then continues. After that, 1, 2, 3, etc. Then the particle then keeps travelling to the right. Okay, so that's what happens with this particle. Again, you can look at the gradient of the graph. Here the gradient's negative, so the velocity is negative, it's travelling to the left. Here the gradient's all positive, so the velocity is positive, which means that the particle is travelling to the right. So here, this section, velocity is negative, so travelling to the left. Okay, here velocity is 0, so the particle has stopped. Here, for this section of the graph, velocity is positive, so therefore it's travelling to the right for the rest of this section. Okay, so travelling to the right from T1 onwards. Okay, now let's look at the questions. Next page, the question says, now this is the original function, it says draw a sketch of the velocity. As I was saying here, the gradient here is negative, so we've got negative velocity, negative velocity. This is the steepest gradient, and these are that's the smallest, that's steepest. Actually, I'll come to my sheet. Okay, so just coming over here, Don't worry about these values here. We're just looking at the velocity here is negative because it's a negative gradient, but these are bigger negative values, smaller negative values, and then here velocity 0. Then we've got small positive gradient and then bigger positive gradients. And the positive gradients get bigger and bigger as we go up. So to sketch the velocity, sketch the velocity versus time. So sketch velocity curve versus time. We've got, just like this, velocity and time. We start with the bigger negative velocity, and then we end up with 0 velocity. So we start with negative velocity, 0 velocity, and then we have positive velocities. Now the other thing is, this is an x² type graph. Remember that velocity is dx dt. So it's the gradient of the displacement curve. So if this is a positive x² type graph, then if you differentiate x², you get, say, 2x, but of course it doesn't start at 0 because we start with a negative velocity down here. Then here we've got 0 velocity, and up here we've got positive velocities. So the velocity versus time graph looks like this. Next thing we have to do is sketch the acceleration curve. Now, remembering that acceleration is dv dt, or it's acceleration equals the gradient of the velocity curve, of the velocity graph. So the gradient of this is a positive gradient and it's constant, so therefore the sketch of acceleration versus time, so if you have to sketch acceleration versus time, it is a positive velocity and it's constant because the gradient of this is a constant gradient. It's the same all the time, so it's just positive gradients. So therefore that is the sketch of acceleration versus time. Okay, now going back to the original graph, I'll just, I think, go back to the book now. Okay, now the next part of the question, find the values of t for which the particle is at the origin. So if this is a displacement versus time graph, particle is at the origin at time 0 and time 2. Okay, so going back there, question out again, and I'll do it on the paper. It says find the values of t for which the particle is at the origin. It's at the origin when x is 0 and that is at time is 0 and t2. And when is the particle at rest? At rest means velocity is 0 or dx dt is 0. It means that the gradient of this curve, it's when the gradient of this curve is 0, and the gradient of this curve is 0 at t equals t1. Okay, starting the video. Question 3 in the examples, the graph below is the velocity of a particle. Notice we've got velocity versus time. Here we can see down here negative velocity, 0 velocity. This would be the a positive velocity, and then we're coming back down, still positive velocity, but here we've got 0 velocity, negative velocity, still negative. That's the greatest negative velocity. This is the highest positive velocity. In other words, it's the highest, the greatest velocity in the positive direction. This is the greatest velocity traveling in the negative direction. Again, here's 0 velocity, again, positive velocity. So I'm just going to go to my sheet now, and we're going to go through the questions in example 3. Okay, now the first question is to draw a sketch showing the displacement of the particle. Now this is velocity. If you want displacement, it's like we have to integrate this. You can think of that being a cubic. You'll end up with some sort of quartic graph, or these are the actual velocities and you have to sketch the original curve. Now notice that if you did integrate a curve, for example, you would get your answer plus some constant. So we're not going to know the exact, sorry, I need to make this a bit. So we're not going to know exactly where we start the displacement graph, but it doesn't matter how far up or down that it goes. So let's look at our original curve. Here we've got, say, negative velocity, then we've got 0 velocity, positive velocities, still that's the greatest positive velocity, still positive velocities but getting smaller, 0 velocity, negative velocities, this is the biggest value of negative, because remember you're reading it off this scale here, still negative velocities but getting smaller, 0 velocity, and again positive velocities. So this indicates the gradient. All these values here indicate the gradient of the original curve. Remember, velocity is the gradient of the displacement curve. So here we've got negative velocity and then 0 velocity. So in other words, the gradient of the original curve is negative, and then here the gradient is 0. So we've got negative gradient, meaning it must go down. Doesn't matter whether I start up here or further down, it doesn't matter. So I'm going to say start here, it doesn't matter, but negative velocity and then 0 velocity, meaning that you've got a stationary point. So here we've got a stationary point at T1. We've also got a stationary point at T3. And we've also got, when velocity is 0, we've also got a stationary point at T5. So the curve goes like this, and then we've got positive velocity, that's the greatest positive velocity. So we've got a positive slope, but then here at T2 is when we've got an inflection, it's the greatest positive slope, and then we've got another stationary point here where velocity is 0 here at T3. Then we've got a negative gradient, that's the greatest negative gradient. So if we look at the gradient of the velocity curve, see here, the gradient here of the velocity curve is 0, which means that A is 0, acceleration there is 0, here as well acceleration is 0. But we know that acceleration is the second derivative, so therefore you've actually got a point of inflection. Every time you've got velocity here 0, sorry, acceleration 0, or velocity being a maximum or a minimum, say down here, you've got, well, actually this is a maximum velocity but traveling in the negative direction, you've got an inflection. So at T4 we've got another inflection. So we've got, so here the gradient's negative, and as you can see the gradient of this is negative, but you've got an inflection at T4. So we've got concave down, then it'll be concave up. And we've got another velocity 0 here, so another turning point. Now, it doesn't matter how far down I go and do this. So I've got another turning point at T5, and here I've got positive velocity. So we can see this is in the shape of a quartic graph, okay? We've got velocity 0 at t1, t3 and t5, and these are minimum and maxima on the original curve. And where the gradient of the velocity curve is 0, that means that you've got points of inflection, because remember, inflections are second derivative, and if x is your original curve and v is your, if you differentiate you get velocity, and if you differentiate again you get acceleration, and these are x dot and x double dot, then acceleration is the second derivative, and points of inflection on your original curve, points of inflection, we know that for inflection second derivative is 0. Those points of inflection are where the acceleration is 0, or where you've got maximum and minimum velocities, okay? All right, now let's answer the question. So we've drawn the sketch showing the displacement of the particle. Now, the next part of the question says, find the times when the particle is at rest. So the particle is at rest when v equals 0, and we can see when is v equals 0 on this graph at t1, t3 and t5. So that's t equals, so that will be when t equals t1, t3 and t5. And when do we have maximum velocity? Well, that will be the times when the particle is at maximum velocity. So looking over here at our velocity graph, remember these could be, you just take these as values going up. This could be velocity is 5, 10, 15, 20, 30, for example. And down here, -5, -10, -15, -20, -25, -30. So this value here for v is bigger in size than this value here for v. So maximum velocity is when t, so maximum velocity is when t equals t4, but note that the velocity, so it's actually the maximum speed, but velocity here is in the negative direction, or the speed, sorry, that the particle is traveling in the negative direction, that's all. But the magnitude of the velocity will be greatest at t4, but it will be in the negative direction because you're getting velocity is negative something. Now, the last question, explain why you can't state accurately when the particle is at the origin. It's because to find, when we draw the graph of x with respect to time, remember that we are, if you integrate the velocity, you get x, but remember you get x plus c. So therefore this graph will be shifted up or down. We don't know the exact position of the curve. So I'll just show you that somewhere else. Okay, I'm just going to the textbook explanation. It says you can't tell when the particle is at the origin as the graph is not accurate. For example, the graph, that graph that we drew in part A showing the displacement of the particle could be up there. It could be down here. So we don't know exactly where it is, because remember we get the displacement curve from the velocity curve, and if you integrate velocity to get displacement, there will be plus a constant. Okay, so there are many, these are all the possible graphs that you could have, or even there are even more than that. It could be more up or further down. Okay, so we don't know exactly when we're at the origin because you can't tell exactly when you cut the t-axis. So where we cut the t-axis does tell us when you're supposed to be at x is 0, but this of course is not accurate. It's just, they're just possible graphs of the original function. And when we drew the displacement versus time curve from the velocity curve, here we've got, remember that the velocity graph is the gradient function of the displacement graph. So here it's saying gradient is negative, gradient is 0, gradient is positive. So if you've got a negative gradient, a 0 gradient, and a positive gradient, can you see that you've got a minimum turning point? We can do the same, say here at T3, we've got a positive gradient, a 0 gradient and a negative gradient. So we've got positive gradient, 0 gradient, negative gradient, and that gives us the maximum there at T3. Again, here at T5, we've got negative values for the gradient, 0 for the gradient, positive values for the gradient. So negative gradient, 0, positive. That gives us another minimum turning point at T5. with the inflections, we can see that this is the largest, as I said before, the largest value of velocity there. So it'll be the steepest that the velocity will be. And also because A is dv dt, the acceleration is the gradient of the velocity curve. And here we can see that the gradient is 0. So therefore, here is where we've got the inflection, okay? And same with this point here, we've got an inflection there, okay, because it's an inflection on the original curve. Now, when you come to do the exercise, okay, when you come to do the exercise, which is 6.5, exercise 6.5, you'll just notice something. I've just found a little error. And the error is question 4. It says the graph below shows the velocity of a particle. This should not be x here, so that is not an x. That should be v, so can you fix that up? That is velocity, that is time. So if you take that as displacement, you're going to get this all wrong. Okay, so there's an error in the book there. That is a V where I've highlighted there. So just here is a V. Okay, so if you can do these questions, that would be great. And I don't think you'll have too many problems with them. Okay, and we'll continue with motion and differentiation next lesson.